All right, let's get started. So I've got some FATSAT stuff written out here, and we'll start working through some of these goals for today. Before I get to that, I actually have one other thing I wanted to share with everyone. So if you don't know, you can go over to mrforth.com. I have a new article you'll find here, the dynamic linking article. I started this last Wednesday on the stream, and then I worked on it for about a week or like 4 days between that Wednesday and the next and this week. Um, I put into doing some research. So I've got a bunch of info here uh, about how to do dynamic linking on Windows and Linux with various compilers, and also have a giant example repository over here where you've got like, how do you do it on Windows, and what are the rules on Windows, and what does the code look like, and then there's also these cool tricks, how to run code that goes before main. So it's a little bit nasty, but this is a trick that lets you say like, okay, before we actually run that entry point, here's how to write a function that gets kind of hooked in for initialization, which is really useful for things like DLL. So I got a lot of cool stuff in there. So if you were at the stream where I started that, a lot of folks seemed interested to get all the information that I was sort of researching in that stream in one place. So I put it all here on the reference for dynamic linking. And yeah, take a look. Let me know if that is helpful for you. But that's it for that. Let's get to the FATSAT stuff. Um, let's see. We need to put ourselves back into code writing mode here. All right. So let's set the FATSAT test up again to do the hard Sudoku. So build Sudoku constraints. Kings moves off, knights moves off, thermometer. Yeah, so I have it set up here. And let me see. Um, local vars. We're in debug mode still. Okay. So what we found was, I've got my build and my run scripts are not quite right for this project. We don't want to do podcastoscope today. We want to do FATSAT today. FATSAT test is still set up. Is the project set up? No, so we got to switch this back to run fly. All right, load the project. All right, FATSAT builds. Now what we were finding, I'm not going to run it over here because it doesn't complete. Take a look. We put in a problem here, and it starts going, and I let this run for a few hours without any sign of it getting anywhere near finished. So we've concluded that while it does manage to make progress and solve, right, if we go back and recall how far we did get, if I take out the hard Sudoku thermometer and put in an easy thermometer that just goes from right to left in an easy sort of way, if I run that, it just works. So it's not that it can't handle thermometers or Sudoku boards. It's that the hard one was too hard. But it does converge on solutions. It doesn't seem to be getting stuck. It's got too many stages. It's too much computation for it to find a solution to the hard version. But there's a lot of stuff we're doing that is not very optimal in the solver. So let's go to that solver, and I'll point out a few things. And then we maybe want to, as a very first step, do something to instrument it. Maybe not profile it, although we could do that. We could try profiling. I think counters might also be valuable, or even more important, like how many times are we doing, how many times we're doing propagation, for instance. Well, let me show you that. Let me show you the solver. So propagate. So here in our solver, we start off with this idea of propagation. And what propagation does is it loops through all of the clauses, and it finds if any of them are at a point. Now remember, a clause is like a list of variables that are all Boolean. So if these are all Booleans, if this one is false, right, so I'll like mark off the ones we can't actually rely on. So we can't use that. We can't use that. We're trying to get one of these variables to be true. So this is like x1 or x2 or x3. So if we find any clause where only one of the variables is free and all the rest are false, then we're going to have to set that one to true, right? Because the rule is one of these has to turn out true. So that's what the propagation is looking for, is those variables that are determined by the state of all the other variables already. And so it loops through all the clauses, and for each clause it scans the literals and figures out what's going on. And so this is an important part of the algorithm, and it can be pretty slow, right? Like this scanning all the clauses, we also are growing, the number of clauses grows over time. So it starts large, it has to happen a lot of times, and it's doing something very slow. So the biggest optimization that we can do in general is, and what I mean by in general is that applies for whatever instance of SAT you want, is a generalized solution. It is not a heuristic for a specific case. It is not an optimization that sometimes makes sense and doesn't. It's just a nice generalized optimization. Is instead of saying look at all the clauses, what we do is we say, well, whenever we're doing propagation, we actually have some variables that we've already set, right? So right here, for instance, we are assigning some fixed variables. There might also be variables that get set during propagation. So propagation itself might be setting variables. Let's see, that happens. Yeah, you can see right here, if we find one of these clauses with one unassigned literal, then we run an assignment here. So whenever we're doing this assignment, if we were keeping track of what we were assigning, then what we could do is say, okay, imagine I have a bunch of clauses, and this is one of them, and this is one of them. And my most recent move, like everything was settled, and then I made a move. And by a move, what I mean is I assigned a variable. Let's say I assigned x5. Well, then I wouldn't really there wouldn't be any reason, right? If I knew I assigned x5 and I was keeping track of which variables I have assigned, then all I would really need to propagate is the relevance of x5 itself, right? I would go, hey, if x5 just changed, then this clause is a possible clause of interest because x5 appears there, and so it might have just become a clause that I can make a deduction from. But this clause here, x1, x2, x3, if I couldn't make deductions from it before, I still won't be able to now. So there's no point in visiting all the clauses. I can just I can have an index, right? I can say when I've set a variable, go to that variable's index and say, okay, what are all the clauses that are worth checking out after this variable has been set? And so the way you would do that then is you'd have a map that would be like, okay, well, if this is clause 1 and this is clause 2, right, and these go on and on, there's all these clauses, then we would have a map that's like, okay, well, x1 goes to clause 1, x2 goes to clause 1, x3 goes to clause 1. And these might go to more clauses, right? x1 might also appear in clause 9 and in clause 18, right? Or, let's say clause 10 and clause 19. Or what am I doing? Let's do this. That's a good pattern, right? And this might appear here in clause 12 and clause 22 and so on and so on, right? This might appear in clause 13 and clause 23 and then x4 appears in clause 2 and clause 12 and clause 23 or something, right? So it starts getting interesting. There's the index of variable to clause is just as interesting as the index of clause to a list of variables, right? And so then when I change a variable, what I'm going to do is go like, okay, I just set x5 to true. So we would look at x5 and we would see x5 and we would see that the clause 2 is relevant. But then the next thing we could do is we could say, well, okay, clause x5 could be a positive or negative instance of the x5 literal, right? We could have some of these be negated. So really what we could then do is say, okay, well, let's subsort these. So we have two different x5 indexes, one for the positive literal and one for the negative literal, right? And so then this could look like this. And the reason that would be useful to do is if I set x5 to false, then clause 2 isn't going to be a deduction, right? If I set x5 to false, then this clause is already satisfied, so I'm not going to deduce that any other variables have to be true. I make deductions when all of the variables are false or all of the literals have resolved false except for one, right? If there's one unresolved literal and the rest are all going false, then that clause can be used for a deduction. So what would happen is if I set x5 to true, I would come over here and look at this list and go, oh, C2 is a relevant place to look. But I wouldn't look at this list because, you know, we're saying these are the things where x5 appears as a positive literal, and so those are places where setting x5 to true doesn't actually have the potential to lead to deductions. So that's the next step we would do to clean up the index. Okay? Now, we can do this, we could build this, and it would probably be better than what we're doing by a lot. But there's a clever trick that lets us go even farther. Let me take a quick talking break. By the way, happy to answer any questions about whatever I'm talking about here. So if you've been following along, go ahead and send them in. Flexen has a question. Would it be good to save those literals, or on their literals have a claused save? I'm not sure if I understand. Would it be good to save those literals, or on the literals have a clause saved? I'm not sure I understand. Oh, are you saying, hey, why don't we, instead of doing this, do this? We have a single list for x5, and then we mark which clauses are positive and negative. Well, we could do that too. But remember, the way we're using the index is to go, when I assign x5, I'm then going to come here and scan this list to see which clauses have been affected. Now, one way that it might be good to do that is I might start saying like, well, if these clauses are a data structure in my solver, maybe I'll have them marked as some of them will be unresolved and some of them will be satisfied, right? And so I could then go, okay, scan these. C2, when we set x5 to false, C2 becomes satisfied, and C13 and C24 we need to C13 and C24, we need to check if they lead to deductions, right? So we could make a single list here, and we would scan the whole thing, and we would use these marks to just say, okay, anything marked in a way that matches the way we set the assignment, that we can then mark that clause as satisfied. And then anything that is marked the opposite way, we check that to see if it leads to deductions. And if it doesn't lead to a deduction, and it doesn't lead to a conflict, then we can just leave it unresolved and go on, right? The cool thing about that then is when we go, if we were to do this, start marking clauses as satisfied and unsatisfied, then any clause that's marked satisfied, we can just not scan it. So like if we were like, okay, C2 just got satisfied, and then we go to C13 and say, hey, is there a deduction here? C13 might already be satisfied, and then you go, oh, nothing to do here, and then you move on, right? The reason I'm not going to worry too much about the details of which one is faster is because there's yet another optimization that can happen. So this idea is the right idea to get started, but the idea of watchers is that this is still too much, because we can actually use a clever trick that relies on the fact that deductions only happen when we're down to one unresolved variable. And so there's a way to sniff out those moments when deductions become possible with even less data structure to iterate over here, right? So what is that going to look like? Let me tell you about how watchers work. So this part, we read about it in the mini set, and then I also watched a YouTube video. I've recommended it a few times. Let me pull it up again for you if you're watching this one. SAT solver. SAT solvers, this video here, a peek inside SAT solvers. If you look at this video, he describes why watches work pretty well. Let's see. So I think it must be here during unit propagation. So he's showing here, he's got this idea of there being these two watchers on the clause. And if you go and watch this, he'll explain it to you too, but I'm going to explain it here now. I think his explanation is pretty good, and that's where I learned it. That's why I keep bringing it up. But I'm going to explain it here, so you don't have to jump over there and watch it. You can check out my explanation if you want. Let's see how this goes. So let's say all of these, let's simplify the picture. Let's say all of these variables here in C2 are unresolved to begin with, right? Then when we set one of them, right, if I set x4, then this clause is not going to become something we can make deductions off of, right? To put it another way, we could imagine putting a counter on each of these, right? So this has a count of 3 to begin with, this has a count of 3 to begin with. This is the count of unresolved literals in each clause. And what happens is, interesting clauses are ones that are unsatisfied. If we were tracking all this state, interesting clauses are ones that are unsatisfied and down to 1. So like if x5 went false, x6 went false, this would be unsatisfied and have 1 unresolved literal. Then this is exactly the information you need to directly test if this clause is ready for deduction, right? So that's a way you could think about this, is that we kind of could think of it like having a counter. But again, we're not going to attach this data directly. The data structure idea here is going to be a little bit more clever. And the idea is, instead of attaching a data structure like this, we're going to attach these 2 watchers. And we could think of watchers as these separate data structures, the separate list of data structures that are pointing at the first 2 literals in each clause. Okay, so there will be a watcher there, and there will also be a watcher here and here. And then what will happen is, for each variable, I'll have a list that goes let's say we have a list that goes literals to takes a literal in and it sends out a watcher. And so this map would have a x1 to some watcher, an x2 to some watcher, an x4 to some watcher, and an x5 to some watcher. x3 and x6 don't have watchers in this picture up here. These little up arrows that I'm making all look the same, but each one is a separate watcher. I just am not giving the watchers names. Each one has its own watcher, though. And you can think of the watcher as knowing a couple of things. It knows, let's see, how do I want to explain this? It knows what clause that it's living on, right? And it doesn't really need to know anything else, but it also has the correct internal structure to be chained together in these lists somehow, or to be contained in a list like this somehow, right? And so if I'm setting x5 to false, what I would do, and you could think of this, there's 2 different ways you could think about it, but let's say that I make a list that says an x5 watcher lives here. So when I set x5 to false, what I'm interested in is the watchers where on the x5 is true list, right? So x5 is true is an interesting list because I just set x5 to false. All of the things, again, just like when we had a complete index, we're interested in the deductions are going to come from those places where x5 showed up as a true literal, right? An unnegated literal. So the unnegated x5 it in a clause makes that clause interesting to us after we assign x5 as false, right? So the process is assign x5 equals false leads to scan the x5 literal watchers. On the other hand, if we were to do assign x5 equals true, then we would be interested in the not x5 watchers. Okay, so we have 2 different chains here, one for x5 and one for not x5. And we're interested in the one that is the opposite, the one that would become false based on how our assignment looks. So if our assignment is x5 equals false, then we're interested in the version of the literal that has just gotten, that now evaluates to false. And then we scan those watchers, and those watchers take us back to these clauses. So these watchers, you can imagine being just a simplified, short, an abbreviated index, but it's a little bit dynamic. So then the question is, well, how is this good enough? What if x6 gets set? Wouldn't we miss something in clause 2? Right? This is the reason why watchers are initially confusing. Well, if we're missing some of the data, how is this helpful? Well, remember, there's like a count right here, right? There's a count of how many things are unresolved. And if x6 gets set and we miss it, then this, if say we had a counter and we were actually tracking it, then this would come down to 2, right? But it can't come down to 1 and have us miss it, right? If it gets down to 1, then that means one of the 2 watchers must have been affected, right? Even if everything here, even if this went on to 1 billion, right? We would have a huge counter here at first, and all of these could happen silently without us noticing. But before it ever got to the point where it went from 2 to 1, right, at the same time that it goes from 2 to 1, one of these 2 watchers would have to be touched. So we might not visit the clause every time one of its literals is affected, but we're guaranteed to visit the clause in time to make a deduction. And this is actually better than visiting it every time, because if we visit it every time, that's more compute. If we had to visit this 1 billion times, then that's 1 billion units of work. If we only have to visit it once because all of these get set to false, and then one of these gets set to false, that's way better, right? So the idea of the watcher is to do an optimization. Not, some people will say it's on the size of the memory here, which is important, but it's really on the amount of work we do. By shrinking the size of these lists, we're shrinking the amount of work we do, and we're still getting the guarantee that we will discover deductions when we need to. So that's what's so cool about them. Okay, so let's get into a little bit more detail about how we make sure this works. So it's cool as long as these 2 watchers that we have are pointed at unresolved literals. But let's say I set x5 to false, and then I looked here, and this was still at a count 3. So I set x5 to false. I scan this and I go, oh, hey, this is still an unresolved clause because I have x4 is unresolved and x6 is unresolved. So there's no real counter, but we know the counter is 2 now. But now we have a problem, because now if x6 gets set, now we're going to miss it, right? We were worried about missing it, and I tried to convince you we're not going to miss it. But my story about why we're not going to miss it is that these 2, one of them had to be affected. But what happens if one of them gets affected, but it isn't a deduction? Well, in that case, we need to change our watcher. We need to go, okay, well, we need to keep 2 watchers on unresolved literals. So if x5 got set to false, but we're still unresolved, let's move our watcher to x6, okay? And so that would mean we would delete this from our index and add this to our index. So we have to be able to modify these watcher lists dynamically now. So that's a downside. It's a little bit more complicated. It's not a static index that maps literals to clauses. It's this dynamic thing that is intentionally kept narrow, but we have to keep them in sync. So this is where it becomes the kind of data structure algorithm problem where bugs can come up that are about, you need to keep these 2 pieces of the algorithm in sync. If one of them falls off, then you're going to get this kind of bug, and if this one falls off, you're going to get that kind of bug, right? So it's going to be a little bit subtle, but if we get each detail right and we're careful along the way, and then we debug it if there are problems, this still works, right? It's tricky. It's a little bit of a out on the limb kind of algorithm, but it does work. So then we just keep making sure that as long as it's unresolved, there are 2 watchers looking at unresolved literals. Okay? Yeah, Flex, and you asked the question, but that's exactly right. I was in the middle of explaining it while you were asking, but that's exactly right. We need to move the watchers around so that we don't miss things if something changes. Yep. Okay, so moving them has 2 parts. One, the watcher itself now needs to be connected to x6, and 2, the list of the map here that takes literals to watchers has to be modified. Now, that's actually going to boil out to be a pretty simple data structure thing, but doing it at the right time and getting it right is tricky. So there's some other tricks we learned from Minisat. So it turns out we can do it that way, like we can think about it that way, but it's easier to think about it like, okay, the 2 watchers are always the first 2 in the clause. We can actually shuffle the literals inside of the clause freely. The order of the literals inside of a clause are irrelevant. It's more like a set than a list. But since it's stored in memory, it does have an order. So we'll say the first 2 in any clause are the watched ones, right? We're always watching those 2. And so what we do with the data structure then is, instead of having to have watchers that like point to an index in here or something. We just go, oh, okay, x5 got set to false. This clause is still unresolved. Let's swap x5 with x6 because that's unresolved, and now x6 can be watched. And then we have to make the change, right? We still have to make that change over here. So the whole picture is like, if x6 gets, or if x5 is assigned false, but x4 and x6 are both unresolved, we'll come in here and go, okay, this thing is false. Let's take a look and see if anything that is not being watched right now is unresolved. If there's at least one thing that's being unresolved, we'll just take that and we'll say, okay, swap this with that, and delete this from the x5 list and add into the x6 list the C2 watcher that that was originally in the x5 list. So we're taking it out of this list, putting it into this one. Okay. Yeah, Flex, and so the logic is going to initially be very simple. Here's how we initially decide where our watchers are. We don't care. It can be any of them. We are just going to take the first two of every clause. Because the point is, we could try to do heuristics and say like, well, let's try to pick two that are the least likely to be set so that we will have that nice advantage of we only get notified at the tail end, but that is going to be basically impossible. Like, that's a heuristic. I have no idea how we would compute. How we decide which variable to set is also a heuristic under our control, but doing like a global analysis that would figure something like that out seems like more compute for a more dubious reward than just doing the fast, easy thing that works. So at least for now, the goal is just going to be to watch the first two things on each clause initially, and then to do this trick of swapping in unresolved literals into one of those slots whenever necessary. There's some other things we can do. If we discover that one of our literals is set to true, we can swap it into this position. And the reason that is useful to do is because that makes sure that we discover that our clause is satisfied as quickly as possible from then on. We could also try to mark them, but notice one thing we could have happen here. Let's go back to the initial state of the picture. One thing we could have happen here, we're not watching x6. So if it gets set to false, we're not in trouble, right? Nothing interesting has happened. We're just going to make our deduction when one of x4 or x5 becomes false. What happens if x6 gets set to true? Well, we're still not in trouble, but what's going to happen is if x4 or x5, if one of those watcher lists gets scanned, we're going to come to this clause and we're going to say, oh, looks like this watcher has just become defunct. We're no longer interested in it. Let's scan along and, oh, look, this clause is actually satisfied. So we will have to find out that this clause is satisfied later than when it actually became satisfied, which might be a little bit funky, but it's actually fine. Now, like I said, we're actually not going to track if our clauses are resolved or satisfied. We're not going to have a bit on them for doing that. If we did, it might be interesting to do that, and there might be some optimizations to have there, but that might also be a pessimization. The work it takes just to track that might cost more than it's worth to have it. All right, we want to be careful with that kind of thing. We want to be fairly minimal with how much compute we throw in. Because again, this is one of the things that we spend a lot of time doing is propagating. So we're going to go with what Minisat did, because from what I can tell, just looking around in some of the very high level research stuff, it's a pretty good starting point. It is a good balance of amount of compute work to do with the amount of information it lets you work with inside the algorithm. Okay, so that's how watchers work. But in order to get all the way there, we need to change a few things because we are not even propagating our changes based on variables that have been assigned yet, right? I don't have, a part of what this needs is the ability to say like, okay, say I set x2 and x5, and then I get a chance to propagate. Why would I set x2 and x5 before I get a chance to propagate? Well, they could both be fixed variables, so they might both get set right here. Or they might have both been found during another propagation. Say somewhere else I set x20, And x20 led to two deductions, which set x2 and x5. So I was scanning x20, found two deductions, and did both of them before I got to process either one of them. And it turns out we want to do this in sort of a queue-like way. We want to say, when an assignment happens, queue it up and process it after we're done processing the current assignment. That's just an easier way to do it than to say, like, go recurse in and then back out. That might seem more natural to do it recursively, like a stack in this case, but it really, either way, either way, it creates sort of a geometry of when you discover things, and not having like things buried in a stack is a little easier to reason about later on in the process, like when we hit conflicts and stuff. So we need to make some changes to our core data structure for running the solver in order to get there, because we're not doing anything to track which assignments have been unprocessed, right? Our current solver looks like this. It has an array of assignments, and an assignment contains what value that assignment is. So remember, each assignment, how do I want to describe this? The array of assignments has one assignment for each variable, right? So I can say, like, okay, x1, x2, x3, what is the assignment for each of these? And I index into this array to find those. And then inside that, for each variable, I'm finding, okay, it either has the positive value, i.e. the true value, or the false value, or it's unassigned, right? It can be one of those three states. And then it has a guess number, which is the stage, how many guesses we've made in the process of running the solve. And if it is a guess, its deduction clause will be null. But if it is a deduction, then it has a pointer to a clause, which is the clause that created this assignment, basically. Remember, when we're propagating, we find a clause that is ready for deduction. And so then that particular clause creates one single assignment, right? One variable gets assigned from one deduction, which originates from one clause. And so we link those together to remember why we set this variable in the first place, because that lets us unwind those decisions or those deductions later. So that's what lives in an assignment, and we don't really want to change any of that, because it is useful to be able to look into that and see it. But what we kind of need is we need to be able to say, well, when we make an assignment, can we keep track of the assignments we've made in a sort of list? And can we then make sure that we process them, right? If we have this list of assignments that's, I'm not sure exactly what way to picture it, but say it's growing like this, right? And it's starting here, or how do I want to do this for you? It's starting right here, and it's going to go across, right? So it starts here, it grows, it grows, it grows, and then we process this one, maybe it grows again, right? So it's sort of, it's kind of a queue-like thing, like we push some assignments on, we process this one, that generates another one, we process this one, that generates another one, right? So we want something like that. And we also don't need to pop things off this queue. So as we're going along, the stuff we process can stay there. And the reason it can stay there is because later on, we might want to unroll our changes. And so when we are unrolling, we can use this list backwards. So we were using it like a queue for the purposes of processing. But we can also use it like a stack for the purposes of unrolling, in order to kind of take back, okay, we don't want to make any of these assignments, and scan back to some point in the list. And as we're scanning back, that then tells us where are the assignments in this assignments array that we want to undo. So our first step towards this, let's start breaking up this into simpler steps. Our first step is we need an assignments stack. Queue, an assignments list, something like that. And we are kind of mixing at this as both a queue and a stack. So we want to think about how we're going to do that. One way to do a queue is as a singly linked list, and one way to do a stack is as a singly linked list. But to do a list that can do both is a doubly linked list. We might also not want to use a linked list. So let's think about how we would use this data structure. We're going to use it for processing propagation. So popping one thing off of a linked list to propagate is not going to be it's not going to slow us down if what we have to do is a linked list walk. because each linked list walk is going to have a certain amount of, like, the propagation work underneath each step is kind of big, right? So it's a way to think about what I'm saying is we don't want to do linked lists when the amount of work we do per node gets too low. But the fatter the work is for each node, the less penalty the linked list walk has, because the biggest penalty to a linked list walk is the time it takes to wait for the next pointer to become resolved as new data we can work with, right? With an array, you can figure out where the next thing is just by incrementing an integer, which is easier. But in order to read a next pointer, it is a memory fetch that can be a little slower. And so the downside to the linked list is if your work, the amount of work you do per node is small, then you're waiting for these fetches, and if you could speed up the fetches, it'll go faster. On the other hand, if the amount of work you're doing per node is bigger than a fetch, then it makes no difference. The amount, because it can happen in parallel. It can begin the process of waiting for memory to come back, and then for the next pointer, and then get its node processed at the same time in an out of order modern processor. So a linked list isn't the worst option here if it's true. Once this is done, what the propagate loop is going to have to do is go through a chain which itself, each it's going to have to go through those clauses that the literal is attached to. So each literal will have a list of watchers, and it's going to iterate those watchers. And for each watcher, it's going to have to do work kind of similar to this that involves scanning the whole clause. So those clause scans might be pretty fast. But some of this extra work here, I don't know that this would be so fast that the next pointer fetch would really, really hurt. On the flip side, it's also pretty easy to do this stack without any problems, because since there's going to be one slot in the stack for each assignment, or one slot in the list for each assignment, there's actually a maximum number of assignments, which is the variable count. So we could do something like this. This is the assignments array where you put in the variable index and out pops the assignment data. But then there could be like a CECL assignment record, and we would need to come up with better names for these now. But then what we would do is say, okay, for each, right, we have like the record count or something, right? And then we know how many records we've added, and every time we make an assignment, we bump the record count, grab the new empty record on this available list of slots, and fill it. And when we want to unroll, we'll bump that counter down along the way. Then we can have a separate counter for that queue that is catching up with the top of the list. So we could do it this way, and this would just be a fixed statically, like not static, this would be just a fixed array allocated at the beginning of the solve and not need any linked list management. And it would cut down on the pointer, so it would be less memory bandwidth, and it would iterate faster. I think we should just do it this way, because then I don't have to calculate in my head if the linked list is too expensive or not, which I think the linked list wouldn't be too expensive. But since it's easy to do it as an array anyways, I say we do it that way. So let's try to come up with better names for these. So the idea is we have some kind of information. Let me pull up my information sketching board, the scratch buffer here. Okay. So one of our data structures takes a variable ID to assignment information, okay? And another one of our data structures takes the assignment index to a variable. Why don't we call it a variable index? So each of our variables has an index, 0 up to the number of variables, exclusive on the top end. And so for each variable, sometimes we want to figure out the assignment information, what value it has, the deduction clause, what guess number it was when we created the assignment. Other times we want to say, hey, we're making assignments in a certain order. When I make assignment 0, I'm assigning a specific variable. So I don't need the assignment information. I just need to know which variable I assigned. And then when I make assignment 1, which variable did I assign? And then if I unroll, I'm going to decrease the assignment index. But these are the two different maps I need, right? One takes variable indexes to assignment information. The other takes assignment indexes to variable indexes. So what would be a good name for these? So I was just saying assignments before, but I think that can't quite be right because assignments only made sense since this was the only data structure where assignments were relevant. Now these could both, in a way, be named assignments. This could be named assignments because it's the assignment's information that is indexed per variable index. This could be the assignment's information because it's literally the information about which thing was assigned in the, each assignment we create, one of these becomes created. Each assignment we create, one of these becomes created. They're both kind of assignment information at this point, right? So we could call these more like assignment from variable and variable from assignment, right? Of course, the assignment index is different from the assignment information. So this is a little confusing because it feels like this naming scheme suggests that it converts something back and forth. Like it looks bijective. It looks like I put something in one way, it converts that way, and I take that thing, I convert it back. But that's not actually true. This is a chain. You can do a variable from assignment to take an assignment index to a variable index, and then you can run assignment from variable in order to get assignment information. And so if I want it to be fully verbose, this would be assignment info from variable and variable from assignment index, right? That would be the difference. Now the question is, can I make this less verbose? Variable from info from variable. Yeah, these are both, and like the nicest abbreviation is ASS, which is not very nice at all. But is a little nicer, but it's a little less of a nice match for assignment. So maybe I need to rethink why I call this assignment information. This is value, guess number, deduction. That's a good idea. So what if I do assign info from var and var from assign index? Yeah, that's pretty good. I'm actually using var as the abbreviation in other places, so that makes sense. So we would use var for our, this is just var. We can call these assign info and assign index. I think that's good enough. It's a little bit verbose still, but I want it to be very, very literal and still tight enough that typing it out and like parsing it visually works. So let's try those names. So let's see here. Assignment is too big of a name. We're going to rename this to FATSAT CDCL assign info. And let's see, assignment you're fine. You're fine. Here we go. Flexin, the reason I don't want to shorten it, but my only goal is not to shorten the names. I do want to shorten the names, but I want to keep them to the point that if I forget the names that, or if I forget a little bit about how the system works, that the names help get me back there, right? The names I choose are a pathway from my own ignorance to understanding if I craft them well. And so it's important for me to balance between building that pathway and also having something which I can work with. I mean, what I wish I could do is have a non-textual programming system. Yeah, I'm sure you were, but it's important to talk about. What I wish I could do is have a non-textual programming system where I could give things two names, and one of them would be its full name, and one of them would be its sort of shorthand that you use when you are manipulating it a lot. So, like, if you're working with something a lot, then you bring it into focus by giving it really, really tiny names. And all the things you're working with, you're like, okay, here is S, that's the shorthand for the solver, and here's the AI from V and V from AI thing, right? This is the or A from A from V and V from A are just shorthands for assignment info from variable and variable from assignment index. And you just know them all because you've been working with them for the last few hours. So you've just got them fitting on screen in dense ways and you're working with them. But then the next day you come back and you can say, okay, you know what, switch me back to full names. I'm not working with this today. I just kind of want to skim it and get the big picture ideas. And so you want to switch to this other naming scheme. The problem is, even if so in C, yes, you can have certain things with multiple names. You can type def something, you can give a struct another name through something like that. The problem is you still have to encode those particular names into the text. So like if I write right here, I write CDCL arrow assignments. If I rename this to A from V, right? Something like this, right? A from V, right? Today, then tomorrow I would want it to say assignment info from variable. So you have to have some way to have it know which one you want to see more automatically. Yeah, you could try to do this in the editor. I built ForCoder to do stuff like that and realized that that's easier said than done. And not just because of the C language, but the C language does make that extra difficult. Okay, so what we need to do next, we switched in assigned info. Let's keep working on the naming here. So instead of assignments, we don't need this. This is going to be assign info from var. And now all of these need to go to assign info from var. Perfect. Now we also want var from assign index. Okay. Now, when do we first allocate assign info from var? That's right here. Okay. I kind of want to do this. Give myself a little more screen space. Feels a little cramped. Okay, so now we have that list of variables, which tells us which variable we've assigned at each step of the way. So now the question is, can we start using it? And so let's see. Let's try to get it so that the data structure is tracked appropriately first. Why would I need variable count minus one of them? I'm not sure I follow why I would want one less. So Flexen asks, I think if you assigned all the variables, then you solved the thing, so you don't need to follow every single one because the last one is only assigned when you are done. That might be true. So it might be the case that the reason the stack exists or this list exists, I keep thinking of it as a stack because of the fact that it's backtrackable, but it's also being used as a queue simultaneously. So it's like a sort of compound data structure a little bit, but I'm gonna just call it stack because I think it simplifies the point here. When we put a new assignment onto this stack, if it's the last one, well, it's not guaranteed that just because it's the last assignment that we've solved it. It might be, for instance, that we've assigned all the variables, and on our last assignment we found that some clauses are in conflict and that we need to backtrack and make changes. So no, I don't think that assigning the last variable necessarily means that it's a solution. Now, it's probably pretty likely, but I also think on the other hand, even if it was the case that the last one is slightly redundant, I would still probably prefer not to have to write a special case here where I go, oh, wait, hold on, don't do this work. Don't bother with this path if it happens to be the last assignment. Make this path different, divert, do something else. That way we can save one integer allocation in a stack. So I think just saying you can assign every variable through this and the whole, like you can, if you assign every variable once through this API, that everything works and it doesn't have to do anything heterogeneous. It's just the same thing every time. That seems like the simplest thing to me and more ideal than trying to optimize out one integer from the array. Does that make sense? Okay, so this should be good for generating that array, that list of the variables that we've assigned as we assign, but it's not going to work once we need to backtrack. Clause Q. So when we go to do backtrack, where is that? Okay, backtrack is right here right now. It doesn't have its own function. I think I want to pull that out as a function so that when I make changes to assign and to other things, that I can also make changes to backtrack in a sort of single unified namespace, even if it's redundant in the sense that the backtrack can just be called right here. I think having it as an isolated sort of more easily identified code path makes more sense. So this is going to be backtrack number. And so this is going to just get replaced with calling FATSAT CDCL backtrack on CDCL and the learned backtrack number. Okay, so there we've pulled out the backtrack path. Oh, backtrack. Backtrack number, okay. So there's our backtrack path. Now the question is, how do we make this work? It needs to decrease the assign count. Now, right now, the way backtrack works is it achieves its goal of backtracking by running over all of the variables in the assign info from var and unsetting each one that has the correct guess number for backtracking purposes, right? So we're comparing the guess number of every assignment info we have to the backtrack number. Right? And using that to determine this. If we want to roll back this, the really expensive thing we can do is say, okay, before doing any of that, for as long as the CDCL assign count is greater than 0, look at CDCL var from assign index for the current assign count. So we just look at each variable in this stack here, and we go, okay, what is your status? And it goes, okay, I am this variable here. Why don't we grab the assign info from that variable? And then we will go, okay, if this guess number is less than or equal to the backtrack number, we actually can break, right? So we're going back down this stack. The guess number strictly increases, right, in the stack. So the stack doesn't contain guess numbers, it contains variables, but each of those variables has an assignment, and the assignments in those variables have strictly increasing guess numbers, right? So when we find a guess number equal to our backtrack number, that's where we want to stop. And otherwise, we want to mem0 the assign info. So then we want to decrease our assign count. Okay, so that's enough to get the job done. It's not necessarily the best way we could do it, but that gets the job done. Let's build this. Okay, and over here, let's make it run these. Yeah, let's make sure it's running the simple Sudoku and just ensure. Oh, it's crashing. Okay, well, that's why we run it, to test it. Let's pull open our debugger, make sure we're ready to test this project today. All right, and go. For some reason, we're assigning a variable twice. Has that always been happening? Let's do something here. Let's undo well, hold on. Let me take this. I think this is the correct way to do backtrack. So let me say, let's save this over in Scratch for later, because we might want to have that back. But then let's undo everything we did to backtrack back to the way it was a minute ago, which was like this, right? Let's also not deal with the var from assign index right now. And let's run again. Okay, so yeah, this works. There's no bug. It gives us results. We were correct to think this was correct. We were right to think that was correct. But somehow this, and this assert wasn't getting hit, but somehow adding this and this did not work. So before we were scanning all of our assigned info from var slots and comparing their guess numbers to the backtrack number this way, and all the ones that had greater guess numbers got zeroed out. Now we're scanning through the stack and stopping on the first one with a guess number that is equal to or less than our backtrack number. But before we stop, we're zeroing out all of the assign infos. And then we're hitting this somehow. It's a little confusing. Let's take a look at the backtrack logic right here and the assign index logic right here and see how this comes together. Assign count. So variable 0 goes in there and we assign it. Presumably we're going to do that for variable 1 and 2, and yeah, it's going to go on for a bit. So we're building that up. We come here. So we're doing a backtrack. Now let's take a look at the assign count. So we've assigned 144 of our variables. And let's look at a var from assign index on the assign count. So it looks like it's just going to be incrementing in order at first, but then it starts doing interesting stuff here. And we can see it's all filled up. Okay. So then we go, give me this variable here. We're trying to backtrack to guess number 4. So we look at, oh, wait, what? Var assign index, assign count. There's the mistake. I want to use assign count -1. So if I have an array of 10 slots and I want to look at the last one, I need to put that -1 there, right? We're doing zero-based indexing. So there we go. We look at the assign count there and check if this one is supposed to be removed, and then remove it if it is supposed to be removed. Let's see if that gets the job done. There we go. All right, so everything is still doing the same thing. The only change is we have a new data structure for tracking the order in which we made assignments as we go, and not just which assignments we've made. And so now we're using that order to speed up the backtrack a little bit maybe, and it's going to support us in doing more steps. I think I like that suggestion. So you're saying something like name this one pass last, like this? Is that what you have in mind? Young Lane, hello. What I can't do, Flexin, is I can't rename assign count to one pass last. Oh, I could. I'm thinking of, I got this wrong. This would be last. Right. Well, what you're suggesting is assign count becomes assign one pass last. Yeah, I like that. I think that works. That's good thinking. So the number of assignment slots is always going to be considered equal to the number of variable slots. But the number of assignments we've made is sort of a chain. So the number, like the one pass last there. Yeah. Thank you. That's good thinking. Because we're about to do something else where that's going to be help even more with the clarity. For sure. Especially because this can move around, right? Okay. So, by the way, how are you doing, young Lane? Let's see here. Right, so the next step, that's what I was going to write down right here. So we've got our assignments list. The next step is to order propagation by process do propagation by one assignment at a time. Okay, so that's the next step. Your brain is fried from programming all day. That's understandable. I have felt that. I am doing good. I am at the very beginning of my day, so my brain is just you know, we're just warming up the oil. We have not started the frying process quite yet. Okay, so right here is where I am doing my propagation. Right now, the logic of propagation is that there's a loop with a clause pointer, and we're just saying as long as that clause pointer is still pointing at a valid clause, process it, and then iterate to the next one. And if something happens, restart the loop and keep going, right? Let's say that right there, I was thinking of doing a propagation count thing here to see. It's really not necessary though. Like, it'd be kind of nice to stop and get some statistics ahead of time, and then see the statistics change. But I think that's more valuable when you're flying blind. This is actually a well verified approach, so I'm trusting that the research and the people who've worked on this have picked something better than what I've got on my first pass here, right? Maybe later it'll make sense to have counters if I'm tweaking it and coming up with my own advanced heuristic idea. Not that I think that's what's going to happen. I'm not really looking to go into SAT research completely, but what I am saying is I don't see any point in pretending to measure this when, you know, I've already got good reasons to think it's the right direction in the first place. And I also think it's going to keep things rather simple, at least this step. The next step, when we switch to watchers, is a little subtle, but this is not too bad. So let's just zero out this whole version, and we have to write a new propagate. So what we need to do is we have our assign OPL, right? This is the one pass last for all of the assignments we've made. The other thing we want to have is a propagate I don't know exactly what to call this, like the propagate index or propagate cursor. propagate number. The reason I don't want to call it current propagation is because there are big periods of time. So putting time like current or next into a variable is always a little bit risky. And so you got to think about, when does this stop being true? And anytime we're in propagation, then yes, current propagate would be a good name for this variable, because it's the variable that we are currently propagating inside this block. But inside the other blocks, it would be the name for the variable that we're going to propagate next. It would also be the name for the variable that says, how many things have we propagated? Propagated assign I think I'll do like propagation assign index or something like that. Actually, I'm going to call this assign index OPL now that I think about it. And then this will be the propagation assign index. And we'll just have to remember, since we didn't put time in the variable, what kind of the rules are for this particular variable in the algorithm, right? But I think that not putting something slightly misleading is easier for me than the fact that it's slightly missing a time hint. I'd rather not put in any time hint if it's going to be right only half the time, in like half the code, right? And we also have to roll the propagation assign index back when we roll the assign index OPL back. Okay, so the idea now becomes, inside the CDCL solver, as long as the propagation assign index is less than the assign index OPL, then we can do propagation. And we go, okay, here is the variable that we modified. Why don't we call this assigned variable? The assigned variable is the var from index on the propagation index, right? And then so let me think outcomes here. As we propagate, we might find a conflict, we might find a deduction. Deductions just create assignments which extend the queue. Conflicts will end the process, which will require a backtrack. So either way, it doesn't matter. So what I'm going to do is say, we're just going to put the increment right here. Right, we say, have we finished processing everything? No? Okay, then here's how you process this index, and when you're done, increment that and do the next one. Young Lane asks, can ForCoder find all the places where a struct member variable is used, or was it just a global search? No, ForCoder can't do that. So if I look at like assign index OPL, this is just finding all of the occurrences of this identifier. If I picked a, let me see here, I can probably find one that will be ambiguous enough to show the point. Do we have a bare count? Yeah, here we go. If I do count, then we're going to get all the counts throughout the whole code base, right? So there you go. All right, so we know our assigned variable right here. So what we want to do, well, right now we cannot quite do this real because we can't take an assigned variable and use it to jump straight to the relevant clauses, right? So what we're doing here is just sort of testing out the structure of going one assignment at a time. But we don't have any acceleration structure for each assignment thing yet, right? We can't look up the set of clauses. So what we're going to do is just degrade back down to a scan across everything in a sort of sense. Okay. And then we're going to do, our first step is affected equals 0. And we're going to scan all of the literals of the clause we're looking at. We're going to get the variable from each literal. And if that variable equals the assigned variable, then we can say this one is affected and break. So we're just looking to see if this clause is affected. Then, if it is, we'll handle it. Now, once we have an accelerator, what'll happen is instead of, like, this is essentially what we're doing because we lack an accelerator. All the logic we put here is the logic we actually want to do. We want a faster way to discover these clauses, but we don't have one. So we're using a slow way to discover the clauses, and then we're going to write the code the same way we would if we had the accelerator. But we can't quite do that either, because the way we would if we had the accelerator would be this thing of managing the watches, which we don't have. So while we're writing it in isolation from the iteration process that lets us discover the clause, we can't write the final version because we don't have the watches data structure that we would need to maintain as part of this process. So instead, we're just going to do, we found a clause, the same thing we did here. We're looking to figure out this information about the clause. Now, before, the way we figured out if we were done was we kept a satisfied clause count. I don't think that's going to work anymore. So that part isn't the same because we're not actually going to visit every clause like we were before. So we can no longer just count how many satisfied clauses we found. We're going to have to figure out if we are done in a slightly more subtle way. Well, let's see, a conflict. A conflict still makes sense in the same way. We want to break, and now we actually need to double break because we're inside of a loop inside a loop. So let's go to and break prop. I'll put break prop right here. So that's how you break out of all of propagation, not just for breaking out of the clause loop that is associated to this particular assignment, but the entire propagation loop. Um, and when we make a deduction, we don't need this step here. We don't need this step here. When we make a deduction, what we're going to do now is we're going to say, okay, here's the variable that we need to assign. Here's the value we want to assign to it. Here's the assignment itself, which is going to modify our stack of assignment information. But it's not going to affect this loop because this loop is catching up to the top of the stack. It's not popping off the stack as it goes, right? So it's going to try to catch up to the top. It's going to have to go a little farther because we made a new deduction. And we don't need to talk about satisfied clause counts. So we make a deduction, but we actually just keep going. We keep scanning for this particular assigned variable. So when we make a deduction, instead of saying restart propagation from scratch, we say, okay, we'll just keep going. We're moving forward through assigned variables now. So this is a different pattern for propagation, right? It was originally this idea of we're trying to do a pass across all the clauses, and every time something comes up that interrupts the pass, we restart the pass. Now we have an assigned variable. We're looking at the effects of that assigned variable. And when we're done, we look to the next assigned variable, but we don't interrupt the process just because we made new deductions. We still interrupt the process if we find a conflict, but a deduction, we just note that and we say we'll get to whatever effects it has downstream in this propagation. Now we can do less restarting the process. Okay, so this might already be an optimization now, because even though we're doing loops over the clauses, we're not doing a loop over the clause for each deduction, we're doing a loop over the clause for each assignment, which might be slightly the same thing. I'm not sure, but it might be better. I'm not quite sure. I'm not quite sure if it's faster, but at least it's structured better. So we're gonna keep the old one. Now the hard part here is we need to figure out how we're going to know if it succeeded. And the reason I call that hard is because it's not good enough to just say, did we get to the end without any conflicts? Because we might have gotten to the end without any conflicts, but still don't have enough assigned information to actually satisfy all the clauses. We also could say, well, did the propagation assign index just reach all the way to the point of being equal to the assign index? I think that might be an easy way to do it. If we got no conflicts, right? If we have propagated all the way to the point where every single variable has undergone this process, and if our path is still undetermined, so it didn't become a failed path, right? Then we can promote the path to success, okay? So now we're checking for complete success by looking at how many variables we've processed. And if we process all of them and we didn't find a conflict, then that means we've succeeded. Okay. So did we speed it up? I don't know, but did we break it? Absolutely. This is wrong. Super, super, super not right. Okay, so just to double check that the problem is somewhere here in this block and nowhere else, just turn that back off, turn this back on. Okay, so let's try to figure out why that doesn't work then. See if we can understand what went wrong. Okay, nothing here. But sooner or later, yeah, so we've made an assignment somewhere. So now we're going to take a look at how that works out. We're scanning all these different clauses, trying to figure out which ones are affected. If it is affected, we come in here. All right, let's see what happens in a couple of the interesting cases. Okay, so we're making a deduction. How many? So we've only made one assignment so far, and now we're making some deductions. That's good. That makes sense. Because usually it makes an assignment to like put a 1 in the top left corner, and it can immediately make some deductions about how ones can't go in other places, and then how other numbers can't go in the top left corner. So it's grabbing the next variable. Yep, this is the variable that would put a 2 in the top left corner. It's saying this needs to be false, and it's assigning that. So we create an assignment. And now let's take a look. CDCL propagation assign index and CDCL assign index OPL. And every time we do this, yeah, this is going up. So we're making assignments, but we are not finished propagating the first assignment yet. So all of these assignments we're making are just things we've deduced because of the first guess we made. And then we come in here and we're processing our second assignment, which was our first deduction. And so then it comes in here. Its job is to figure out which clauses are newly interesting. Nothing. It makes the deduction here. Very cool. So sooner or later, it's going to come to a conflict. Let's see if that part is a problem. So it jumps out of the loop. It doesn't think it succeeded. Okay, so that's not the problem. It knows that it failed. So it's going to go to the learn clause, and it's going to try to learn. Okay, so let's see how learning looks. Backtrack. Hold on. This might be the problem right here. I bet you backtrack is the problem, because it's going to do this, right? So it just didn't backtrack the propagations. So when we do backtrack, we are rolling back the assignments. We need to roll back the propagation assign index too. It's just a clamp, I think. This should never be larger than this, right? So anything we backtrack, anything we don't backtrack, the propagations from it, we can leave in place. Oh, that gets a little funky. No, I think it's fine. I think it's fine to do it that way. We got to watch out for that. That could get funky. I think it's fine the way it all fits together. But, yeah, so Flexion's asking, wouldn't that possibly assign it to OPL? Yes, it could, but that would be correct, because remember, we've just rolled things back. So if we've propagated 20 of our variables, and we had assigned 30, and then we roll back to 15, then we're going to say, well, we had propagated 20 variables, but we've just rolled back to the point where we've only actually assigned 15. So we're going to want to roll propagation back to the point where it's not farther than the things we've assigned either, right? Like we want to get back to the point where everything that we backtracked is erased, including the thought that we've propagated certain things. When we basically, to put it another way, I don't need to roll back propagation farther than I roll back the assigned index, but I need to roll it back at least that far. Like wherever assigned OPL ends up, that is the cap on where it is even that is the cap on where it is meaningful to talk about an assign index. No, it's valid for it to be OPL because that just means we've propagated everything. right? If it's so it could make sense to say like, oh, propagation assign index should never be equal to OPL if propagation assign index can never reach the end. But it can. It can get to the point where you've propagated everything you've got, like all of the assignments you've got, and that you're not done yet, right? So there's one spot where it ends, where if propagation index gets all the way to the end where it's propagated all variables, that's how we know we've succeeded. But if it propagates everything we've assigned, but it hasn't concluded, but it didn't conclude any conflicts, that just means we need to make more guesses. That's what I think is happening, at least. There is a little, I am sympathetic to what you're saying. There could be a case where that is important to go back one further. And I'm not quite sure like if it is or isn't true, but we have to be careful how to look at this part. So if we look at when we backtrack, I think it'll help. When we backtrack to a certain backtrack number, we have also just learned a new clause, right? So when we learn a clause, we actually make a deduction without using propagation, because the learned clause comes with, like the way it is structured, it always contains the information necessary to create a new deduction. So when we learn a clause, we look here and we go, there's a learned clause. There's also a learned deduction from this clause, or from this learning process. And so even if even if propagation index is equal to the end right there, we're going to make an immediate deduction, which is going to create a new assignment, and then that needs to get propagated. Now the question is it possible that the thing before this should also get repropagated? And the answer is maybe. But I don't think so, because I think the only thing that will be new is this learned clause, and the only way this learned clause is going to make a difference is to create this assignment. So we're sort of preemptively knowing that that's the only new thing and doing it here instead of during propagation. So we really kind of expect propagation to resume from the spot we backtracked to, or possibly from earlier, but I'm not sure how that would ever happen. I'd have to think about that. I think propagation must actually always backtrack to something before we're propagating. Like, I think that's always, I think the fact that I'm using clamp here might actually be conservative. It might actually just be a logical necessity that this would always be correct. But I'm going to just play it safe for now. Think about that other possibility of whether propagation can actually be behind the backtrack at all later. Wait, let me think. No, I'm thinking about it. That's just like, it certainly has to be the case that this is correct. I'm like pretty much convinced. Okay, so there's our fail. Do we have a breakpoint inside of... Okay, no, let's get rid of those first of all. We want to look at... Wait, why is this podcastoscope RB? Did I didn't mean to do that. Let's change something here. I'm going to just say, whoops, sorry about that. Podcastoscope, you're going to be in a weird state next time. We mean to be debugging with the FATSAT project. I have this mistake I make with Remedy a lot where I change what I'm debugging with this button instead of with this button. And so then it like messes up my projects pretty bad. I do that a lot. I don't really like that you have to have all these separate project files in Remedy. Maybe this is the thing I need to learn how to use more application and parameters. I'm not sure. Anyway, for now, look at these breakpoints don't make any sense for FATSAT either. They're clearly inherited from other projects, sucrose and stuff. Okay, FATSAT. Let's go to FATSAT. Font types doesn't need to be here. FATSAT. We're looking at backtrack. What do you mean you didn't find backtrack? Is it in this file? Can you just find it in this file? Okay. So it comes here. This is pushed back to here. we make a new assignment, and then we're going to go to propagation. So immediately there should be something new to propagate because of the learned value of the variable we just got. Sooner or later, it might find a clause which is affected. And so it might, let's see, one way or another, it's going to come out here. Okay, so there we go. It's making progress again. Run. We don't need to keep seeing this. Let's see if that appears to be doing the right thing now. Nice, it's back. Okay, so that's cool. So we've restructured propagation to now work as if it is processing one assignment at a time, which it is processing one assignment at a time. It's just that the way it processes an assignment is to process all of the clauses. So it's not really clearly an acceleration yet, but it is structurally correct that way. Set up watcher data structure. All right, so the next step is we need to set up a watcher data structure, and then we need to drive propagation from watchers. We need to maintain watcher data structure during learning in between those. Okay, so we talked a little bit about what the watcher data structure needs to look like, but let's get more literal about it now. So first of all, the way we want to be able to look for a watcher, when we go to use the watchers, what we're getting is a list, right? Ultimately, we want to get to the point where it looks something like this, where I go, okay, for FATSAT CNF watcher equals CDCL watchers watcher index or something like that, right? Watcher does not equal 0, watcher equals watcher next, something like this maybe. And then what we're going to do is we're going to say, okay, if that's what we're going to do, how do we get the watcher index? Well, that's going to have to be, let's look at the FATSAT, I'm going to put it in here, FATSAT assign. I did have one cool idea. Okay, there's one acceleration we can do. FATSAT CDCL assign info equals CDCL assign info from var assigned variable. Okay. So the reason I want that is because then I can pull out the value and make a literal by doing this. Assigned lit from, or var from lit. If assign info value equals -1, or rather is less than 0, I guess is what I can do, then the assigned literal, we can mark it with a negation right here. So now the assigned literal is I'm ignoring this, what I was doing. I'm doing an acceleration idea right here. So what we want to do is as we look at each literal in a clause, the affected clauses can be narrowed down. Instead of saying if this variable appears inside the clause, then deal with it, we say if this variable appears inside the clause and if the assigned literal, actually we can go even a step further. We can go, here are the affected literals, right? So the affected literal will be the negation, the opposite of what we did. So if we assign true to the variable, then the affected literals are the negated ones. So true assignments lead to negated affected literals. And if we assign false to the original variable, then we want to go and find all the spots where that variable showed up as a non-negated literal, and so then we don't apply this, right? So the affected literal is the flip of the assigned literal. And we're just saying, okay, look at each literal, and if that is equal to the affected literal, then go ahead. This is narrower and faster to check. That should still be correct, though. Nice. Okay. So we can actually line this up like that if we want. But I'm not going to do that because I want this assign info. So then there's a question of the watcher index. And it would be cool if the watcher index could just be figured out from the affected literal. The problem is the way I designed these isn't quite right. So rearrange these bit patterns so that the literals act as indexes into the maps on literals. All right, it's kind of a maybe a mouthful, but I know what it means. That'll help me. The point is, I'd like to get to a point where if I know the affected literal, that I could just use the affected literal right here. I can't do that because I'm setting the high bit, so it wouldn't line up. Instead, what I'm going to have to do is say that the watcher index is created by going let's do affected literal, shift it up 31 once, so we are bit shifting out that. And then we can bring the affected literal down by 31, so I'm rotating away my mistake for now. The affected literal is the one I'm interested in, but I put the negation bit at the high end, and so now I'm rotating that to the low end so that it actually is like each variable will have 2 slots in the watchers array, right? So for each variable there are 2 of these slots in the watcher array, and each of those 2 slots, the first one is the positive one, the next one is the negated one. Flexen asks, what are those literals used for? Can you use them as a flag field plus mask for the watcher index? Hopefully my description of that situation made sense. I was just describing that. But like, I'm going to want something like this, right? Which means that in the CDCL solver's main data structure, what we're talking about is having a CDCL watcher like this. And so there's 2 watchers for each variable, and it's actually going to be an array of pointers, right? So then once I know my watcher index, I go in there, I get out a watcher, and then I walk the chain of watchers, and that chain of watchers would then get treatment kind of like this, although a little different because we'd also have to maintain the watcher data structure at the same time. But like, that's what we're shooting for. So let's see what we can do on this side now that we've made some sense out of that. I think right here, we're going to want to say FATSAT CDCL watcher looks like this. And A watcher is going to need to be a chain, so a singly linked list. We're going to have to watch out for this because we're going to want to be able to remove watchers, and removing things from singly linked lists is a interview question. In other words, it's a way of saying it's overly difficult for something that seems deceptively simple. Easy to make a bug, but the alternative of going to a doubly linked list just to avoid the bug is also bad. So yeah, we'll just keep an eye on that, figure out the simplest way to organize it as we go. And then what does a watcher need to know? Well, it needs to know which clause it's dealing with. So in my system, we do that by having a clause pointer. Now you'll notice this could have maybe just been a clause ref. Watchers could just be clause references, possibly. But I think watchers might evolve. In the mini-sat, they had another thing here that was like the blocker. And I think this was an optional additional feature of the watcher that we're not building right now. Based on how I understand it, it should work without it. But if I want to, the watchers might want to evolve. They might want to expand in some way or another. They might not want to be coupled in with the clause ref, which, what do we actually use clause refs for? Clause Q push. We use them during the learning process. Makes sense, makes sense. Okay. Okay, so the next steps are, let's allocate that array here. Watchers are going to come from FATSAT CDCL watcher pointer variable count times 2. Okay, so we start off with that array like that. Now we need to construct the initial watchers. And in order to do that, we need to go through each clause in the formula. So we look at our CNF formula and we see that, okay, that's going to look like this. We need one of these as our clause, starting at the beginning of the formula, going through everything we've got. And for each clause, what we're going to do is we're going to look at the first two we're going to make a watcher for each of the first two literals. So that's like this. What we can do is, if the clause has a literal count of 1, then we're not going to make watchers for it. We're just going to immediately assign it, because the watchers make a special assumption that we can have 2 watchers, but literal clauses with 1 literal won't be able to do that. So regular old propagation won't find them, but we can do something different, which is we can just assign them the same way we do with assigned fixed variables. Since we've already done assigned fixed variables here, we know we can just run assignments during guess level 0, and it makes sense. So if we find a literal count of 1, then all we have to do is assign that the clause, we want to pull out the variable from the literal. So there's our variable. And we want to figure out what value it's going to have. And now, I don't know if it matters if we want a deduction or not. We could say that there's a deduction clause equal to this clause here. But this is going to happen at guess level 0, so it can never be backtracked. It can never be contradicted without creating a full-on unsatisfiable result. So it doesn't quite matter, but I think I'll just put it in there for now because I'm guessing one way or the other it doesn't matter, but why not just keep the information so that if I see it in a debugger, I can make sense of what I'm seeing. So that's if the literal count is 1. If the literal count we ever find is 0, I think for now we'll just assert that that is a badly formed formula. And so then finally, we have a situation where there are at least 2 literals for us to iterate here. And so what we're doing is looking at the literal. We're saying, okay, give me the inverted literal by doing lit XOR the negation bit. And then the reason we want to do the inverted literal, so say let's look at this. Say I'm looking at a clause, x1, x2, x3, and I put a watcher here, right? So this is clause 1, and here's our watcher on x1 and our watcher on x2. Then what I actually want is that whenever the affected literal is not x1, that corresponds to the situation where the thing we assigned... Sorry, let me think about it this way. This matters when x1 gets assigned false, right? So in this case, x1 is the affected literal. I think I don't want to negate it. I think I want to keep the original. I want to say you'll find in the x1 list C1. So if I set x1 equal to false, then I will if I set x1 equal to false, then my affected literal will be the x1 positive literal, and then I'll want to find clause C1, right? So whatever literal I see in the clause, that's the literal I use to store the watcher. So then what we want to do is do something like, we want a new helper here. I think we'll put it right here. It goes like this: FATSAT CDCL add watcher. And I just go CDCL clause. Let's give it the FATSAT CNF clause. And I want to give it the FATSAT literal. Right? So that's how we construct the initial set of watchers. It's by doing this. So let's go implement that part. That is just now a simple data structure construction routine. We go FATSAT CDCL watcher. Push that onto the array. What array? The CDCL arena, of course. CDCL does have an arena, right? Oh, it doesn't. Okay, in that case, we need to get past it the arena. That's easy enough. Create one watcher. Now the watcher needs to be assigned the clause that it comes from, and it needs to be pushed into the... Right, so we want to get the effect, the watcher index. By doing that rotation we did before, literal goes up 1 or literal goes down 31. Okay, got that resolved. So let's see here. We want to do add the watcher and then get the watcher index and then do CDCL watchers watcher index and push the new watcher onto that. So each slot in this array is the head of a chain. It's a pointer to a chain. And I am here saying attach this to that chain, right? This is a chain of nodes. This is the pointer to the chain of nodes. This is this is a new node for the chain. Take this node and stick it onto this chain. That's what I'm doing, right? So now the question is, what arena does this run on? And I think the answer has to be on the Scratch arena, right? Because the CDCL itself is on the Scratch arena. And that's why it doesn't carry its own arena, because it's running off of the Scratch, the local Scratch. That makes sense. Okay, so that initializes the watchers. Now, let's take a look at our to-do here. So that works, but whenever we learn a new clause, we're going to want to do similar logic again. So here we're just going to say if the learned clause has a literal count greater than or equal to 2, then we do this. If it only has a literal count of 1, then what's going to happen is we're going to assign it. We're going to take that as an assignment. And I think, let's just put in a safety check here. I'm pretty sure that this is how it works. If the learned clause has a literal... Do I have an assert implies? No. Okay, so either it is not the case that its literal count equals 0 or equals 1, or it is the case that the backtrack number is 0. So the reason this is important is if I have a clause with one literal in it, then that needs to be a deduction that is invariant. It cannot be the case that I ever backtrack that deduction. If I could backtrack that deduction, it would be because the backtrack number was larger than 0. But in a case like that, I would then lose the ability to see that clause, since the way I see clauses is by having watchers looking at them. And I can't put watchers on the clause like this. So I'm pretty sure we already concluded logically that this was the way it works, that if I get a clause with one literal in it, that it must have backtracked to the beginning, because to have one literal is to say that we've determined a way a certain variable must be set. And that means it's not contingent on any of the guesses. No matter what you've guessed, what we've learned is definitely true. And so this variable must be set this specific way. And so the only way you could know that for sure is if you've concluded that all of the guesses are irrelevant. If it's contingent on one of the guesses, then what you learn has two pieces. It's like, oh, if the first guess we ever made is true, then this works. But we don't know necessarily what happens if that thing goes the other way, right? Those are things that can then be watched, and we don't need to worry about what backtrack number they are on. But if it is so narrow that it's a conclusion that transcends any guesses we've made, then I think it also has to backtrack to 0. I think that's what we had concluded last time. But I'm not sure, so that's why I'm putting the assert in here. I might need to figure out what to do with this by reading minisat again, but I think this is the right idea. Ones can happen, but they just become assignments at deduction level 0 or at guess number level 0. And then the backtrack number has to be a 0 in that case. And otherwise, we add new watchers based on the learned clause. Right? So we just say, okay, here's the new watchers for the learned clause. So that should be good. Let's see that run. Yep, nothing has broken yet. I wouldn't expect it to. We're just adding a simple data structure that we never read from. So what could happen, right? Now we want to get back to propagation, because this is where it's suddenly going to start mattering. So our goal now is, instead of propagating this way, it's to propagate this way. So we are going to scan the watchers that are on the affected literal. And each watcher, what does it contain? Well, it just contains a clause. And it contains a clause that's going to meet this criteria that we had before for is affected. So we can kind of skip to something kind of like the is affected block here. Okay, but let's review this little bits at a time. So first of all, we need to pull the clause out. Here's the clause of interest. It's the one that lives as a pointer on the watcher. And then what this is currently doing is scanning the whole thing and figuring out if it is in conflict or if it's a deduction. Now, we're actually in a situation where we know it's either a conflict or a deduction, or we need to modify the watchers, right? That's the other trick here. So this is where it's going to get a little more difficult. Okay. Let me look at my time here. I do want to go for another hour or so and get this done, but I'm feeling like I should probably tend to something else. What I'm going to do, we're going to pick this back up. I'm going to need to take like a 30-minute break and stop the stream to deal with a couple of things. And then we'll be back and we'll do this part. So let me just mark this up here. This is what we're doing, okay? I will be back in about 20 or 30 minutes. All right, see you in a bit.